Welcome to Math 106, Chapter 1.3, where we talk about derivatives and limits. Now that we can recognize what a tangent line is, which to recap, a tangent line is where on a particular point, so one particular point on your function, we are trying to find that slope. Therefore, once we have your slope and your point, we can figure out what the tangent line is in itself. That would be the line in red. So now that we know what the tangent line is, right, we can work on how to find or derive the tangent line for any sort of curve, because you might not be given this visual aid to see, and instead you're just given some sort of a function. It might not always be as basic as y equals x squared, which graphically we can plot very quickly, right? Sometimes they'll be a little bit more complicated, which is why we want to use derivatives. So this process is called the derivative. And the process is called differentiation. So you might hear me say differentiation or derive, right? We're just going to say, okay, this is what the process vocabulary is. So to take the first derivative, because you can derive many, many times, in order to derive, we go from the original function into your first derivative. This little prime symbol right here, it looks kind of like an apostrophe symbol in English, right? This is just how to say your first derivative. This whole thing right here, this is how you say f prime. It's not that it is going to be a prime number. It's just, again, how you can say certain things. You can either say the first derivative or f prime. And we just talked about, hey, you can have, you can keep taking the derivative. So if we had more of these little prime symbols, right? This is the second derivative now. You have two of those little prime symbols. This is the second derivative. So this is called f double prime. I use those a little bit frequently. So if you hear me say f prime or f double prime, it's just stating that we have taken your first derivative or your second derivative based on what the context is of the problem. So it does go on to say the more derivatives of that function to take, the more little prime symbols you have. In this case, we have 3 here, so this would have been your third derivative. I don't go too crazy. The third derivative is pretty much where we stop, but you can, again, for some purposes, you can keep going. But typically the third is sometimes the most you need. Now, there are different rules, and there's lots of rules depending on the type of function you have. We'll start with the power rule when we talk about linear functions. Linear functions being the most basic, sometimes even the constant rule as well, again, most basic. So it says, while there are many rules for derivatives, the most basic is the power rule. There we go. It's pretty simple. So it says, f of x is equal to mx plus b. Then for your first derivative, f prime of x, and I'm just going to give it to you first. This is just equal to m. Now, when we go to derive, we're deriving your variable. So your variable here being x, I'll state it here, we derive the variable. Now, b, well, yes, in its current state looks like it's a variable, right? But what is the name of b, right? It's a y-intercept, but what is the y-intercept at the end of the day, right? It is a constant. B is considered a constant. It's called your constant because no matter what your x is doing, x could be 1, it could be 0, it could be 5, it could be negative 100, right? It's always going to affect this m right here, right? This term will be affected by whatever value x has been chosen. But at the end of the day, b is unaffected by it because it's not being multiplied by the unknown x. Therefore, b, whatever number it is constantly going to be the same. It's not going to change. It's unaffected. So when it's unaffected, right, when we look at your function, right, a constant function here, f of x is equal to b, it's a horizontal line, right? If we said f of x is equal to 4, if we were to graph that really quickly, right, that's just y is equal to 4. But what do you know about your slope here, right? Well, your slope for horizontal lines are at 0. So with your slope of that particular constant, right, is at 0, when we go to derive it, the first derivative of this constant, right, a value that's unaffected by your unknown variable, therefore will be 0. And that's going to always be the case. So it says, therefore, any constant, any value that is unaffected by your variable x or your variable, whatever it may be, the unknown, it can and will be dropped. So your constant, and it goes on to say the derivative of a constant function, f of x is equal to b, is 0. Therefore, when we actually write your first derivative, it's equal to 0. So that is in short, or in like a roundabout way, just saying that here we're going to just drop it and just say it's 0. Now, the reason why m is behind is that when it's to the first power, right, x right here being linear, it has a degree of 1. We're going to each time subtract, and we'll see this here in a second about your formula, we're going to subtract 1 every time from your degree of your variable, right? So in our case, if we have mx to the first power, and when we go ahead and subtract that 1, right, 1 minus 1 is 0. Well, what do we know about any exponent raised to the 0? Well, this turns into 1. So m times 1 is just m. So for your equation, right, if we move up in the power rule from linear, the structure to quadratic, cubic, quartic, and so forth just says that whatever your value or whatever your exponent is, we're going to drop that exponent first. So we have your f prime of x, so your first derivative of x, is equal to the a that you've dropped times x, and you're going to take that initial a and you're going to subtract 1 each time, just like you did up here. So 1 comes down, and it, because it was a 1 to start, it doesn't affect anything. But then you subtract the 1, and then you can evaluate. So for linear functions, it's just always going to be m. For quadratic, cubic, quartic, and so forth, it'll be a little bit more not involved, because power rule is the most basic one, but you'll get the hang of it. So let's go ahead and in words, just briefly describe what happened. So we said we dropped the exponent. To the coefficient. So that's step 1. Number 1, we dropped the exponent into the coefficient. Step number 2, we subtract 1 from the exponent. So that would be right here. And I want to put an extra thing up here, coefficient and multiply. So when I mean multiply, if you already have a coefficient, we'll multiply a by the other coefficient. So let's get the hang of it. So let's maybe try A and B together, and then you guys can go ahead and try B if you pause the video. So let's take a look at A. We have negative x to the 6. So first thing, what is it going to do? We said, okay, well, step number 1, we drop your exponent and multiply. Let's drop your exponent. We now have negative 1. I'll just show you where the negative goes, times 6 to the x. Now, step 2 says that we're going to subtract 1 from your exponent. So it used to be 6, and now we're going to subtract 1. So we have, now we just have to kind of clean it up. We have negative 6x. 6 minus 1 is 5. This is now your first derivative, f prime of x. And there you go. Let's try it again. So step 1 for your first derivative, x. We're going to drop it down and multiply. We're just multiplying by 1 here. Then you have x to the 12 over 5. And again, subtract 1. Now here your 1 can turn into, instead of showing a 1, we can do 5 over 5 to get a common denominator. So we can go ahead and subtract those. 12 minus 5, well, that's 7 over 5. So again, this is your first derivative of your function. Now see if you can pause the video and try it all at once, given something that's a little bit more expanded. So when you have multiple terms, you get to do the power rule for each term individually. So let's take a look at that process once more. So on all of these, the very first step we're going to do is drop each exponent down in front. Now, what's the exponent of this x if I were to put it in? Well, it's going to be 1. So I'm going to drop all of those terms. So you have 4x, and now we take your 4 and we did what to it? Well, we subtract the 1. Minus 5 over 3, x to the 5 over 3. And again, subtract the 1. In our case, instead of subtracting 1, let's put it into a fraction, 3 over 3. Plus 1, x to the what? 1 minus 0. Now you have negative 5. What's another word for this negative 5 if we were to have graphed it? All right, well, this is your constant, right? This turns into what value? This turns into 0. So whether you add or subtract or 0 doesn't really matter. I'll just say minus 0, but that 0 will go away. So now let's clean it up, make it look a lot nicer. We get 4x cubed minus 5 over 3. X, let's see, 5 minus 3, that's 2 over 3. And then we have x to the, oops, I kind of wrote that too quickly. Should be 1. 1 minus 1 is 0. Anything to the 0 power is 1. So this 1 drops multiplied by the 1 that the x would come out to be. So it's just 1. And we can go ahead and eliminate the 0. So this should be your final answer for the f prime. So let's try it one more time with example 2. So it says apply the power rule to find the first derivative. And we're no longer just working with one that is just kind of basically shown out with your power. Sometimes you might have different radicals, which, as we've talked about, what did we learn about your exponents when it's in your radical form? Now, before I get started, I do want to see if you can pause and look at those hints. Maybe you try it out yourself and then you come back. Right, but when it's your radical, right, before we even take your derivative, show your power, right? how do you go from a radical into an exponent? Right? Well, you have your degree here because it's a square root, it's 2, and your degree on your x, because it's not there, it's your kind of ghost 1. So it's 1 here. And what we remembered, hopefully, if we have a x to the b, when we go into a fractional exponent, b stays on top, a comes down below. So for us, 1 stays up, 2 comes down below. So first step, if it's not showing your power in an obvious way, we want to show it to be whether it's a fractional or a negative exponent. So ours is fractional. So now when we do your first derivative, we can then go ahead and drop your 1/2 x and now subtract that 1, or in our case, 2/2. So we now get 1/2 x to the negative 1/2. Now at this point, we might want to clean it up a little bit. Ours is negative as an exponent. So let's go ahead with negatives. What do we do? Well, your negatives, we go ahead and drop them into the denominator. There's already that 2 in the denominator, so they'll just get multiplied together. It's now positive. Let's go ahead and put it back into a radical. Typically, my rule is if it starts as a radical, you want to end it as a radical. If it starts as a fractional, you want to end as a fractional. Typically a positive fractional, though. So let's go and take it one more step further. In order to convert back, the 2 comes out and the 1 stays in. So this would be your most simplified answer of your first derivative. Now let's see if you can try B. Again, your hint here is, what do you know about your exponents? So show your power. This, well, yes, it has a degree of 1 here. Notice that it's located in the denominator. So in an obvious way, we want to make sure we see what your exponent is very clearly in the numerator, which to go from the denominator into the numerator, right? If it's positive down below, when we raise it up, it'll be negative. So you have a negative 1 here. Now we can go ahead and apply your power rule. The negative 1 drops, and then we can subtract a 1. So that just makes it more negative. So now is negative 2. And again, my kind of rule is if it starts as a rational function, so 1 over your variable or a number over your variable, we want to end with it in the denominator. If it starts with it in your, if it starts out with a negative exponent, well, actually, that goes against my rule. I like no negative exponents. So disregard that. I like negative exponents to be gone. Negative exponents down here. And now it's positive. So if there's anything in the radical, take it and put it into a fractional. So we'll write it like that. If in a radical, make a fractional exponent. If in the denominator, put into numerator and change the sign of the power or the degree. So now what we have done here in this process using the power rule is kind of finding the slope in a way of your tangent line. Now, how is that possible, right? It's not an equation, right? Or it's not the equation of a tangent line. However, when we're ready, we're going to find a point, right, that we want to locate on your function. And then using that point, we can go ahead and find the equation of your tangent line. Find the slope of your tangent line and then create the equation of the tangent line. So right here, right now, what we have done is we have the equation, not of the tangent line, but of the slope of the tangent line. Heavy emphasis on the slope of the tangent line. Now let's talk about the geometric meaning of the derivative. So in general, the derivative of f of x at when a, or x is equal to a, is the slope of your function f of x at the particular point when x is a, and then your y counterpart. So this is just an x value, an x coordinate, and this is your y coordinate found on the function. Now, since the slope of the graph at a point A is the tangent line at the point A, then dot, 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 when we talk about the meaning of your derivative, it's just saying that the first derivative of A is the slope of the graph of that particular function at the particular point. So we talked about, hey, this is really the slope of the tangent line. So when we go ahead and pick out a particular point to evaluate, this could be when x is equal to 1, or when x is equal to 2, or when x is equal to -4, right? Whatever it is in your function, we can go ahead and determine at that particular point, we can go ahead and find your slope. So the slope of the tangent line to the graph is at that particular value. And again, I break it down. What does this mean, right? It's a lot of words, it's a lot of math. So let's break this down one more time. It just says the derivative when x is a, so you've picked out a point, x is now a, provides the slope of the graph at a, when x is a, whereas f of a, right? This is when this is your y coordinate when x is a, gives the height of the graph again at a, at the point that you have picked. So not all of your graphs are going to be nice and uniform or symmetrical like this. So we'll have lots of different outcomes when we look at a particular curve. So let's go ahead and compare the slopes on your graph. Which is steeper, x is equal to 1 or x is equal to 2? Well, x is equal to 1, right, is this one in red. And notice that it's the tangent line when x is 1. So if we were to graph real quick, when x is equal to 2, that would be here. When your y value is 4, if I'm drawing a line here, my tangent line, as best I can, just try and make it go through once. There we go. Which do you think is larger or steeper? Right, well, the blue line is going to be steeper than the red. So if we wanted to find numerically and see kind of a good argument for it, can we take the first derivative of x squared? Well, your power rule says, let's drop your 2, and then we have x, subtract 1 from 2, and we're left with 1. Now, we said a moment ago that we have the equation of the slope of the tangent line, meaning that this is the slope of your tangent line, or the equation of the slope of the tangent line. So when we're asked to evaluate which one is steeper, we have an x. We want to compare when x is 1 and again when x is 2. So taking your first derivative, f prime of 1, and plugging in the 1, into your first derivative function, we have 2 times 1, which is equal to 2. This is the slope of the tangent line when x is equal to 1. And so we should see a difference when we do the same thing when we plug in a 2. We take now the 2, we plug it in. 2 times 2 is equal to 4. So this is now the slope of the tangent line when x is equal to 2. And your tangent line will change based on the points that you select, unless it's, of course, a line, in which case it's a constant rate of change, right? Therefore, it's just its own its own slope, right? The slope of a line, right? If you're looking for a tangent line, no matter where it is, it's just itself. It's not changing. Whereas here, your curve is changing, therefore your outcomes are going to change. So note, using the derivative, we can find the slope of the tangent line to find an equation of a line at a given point on your graph. So for example 3, it says find the equation of a tangent line from above. Oh, and actually we already did that point, right? So we're doing it with once from at the point 1, 1 and 2, 4, right? Well, we did it before. We said step 1, take your first derivative. If we're starting with f of x is equal to x squared, your first derivative, as we did previously, is 2x. Now the next values are kind of breakdowns. So step 2, use the x value of the coordinate and plug it into your first derivative. This is your first derivative here. This is the actual slope of your tangent line. So your point 1, 1. This is when your x is equal to 1 here. And I'll highlight so you can kind of keep track of what we did previously. So f prime of 1 is equal to 2 times 1. Which equals 2. So this is the slope of your tangent line. At the point 1, 1. Let's do it again. Kind of repeat that process. We said the point at 2, 4 when x is equal to now 2, because again, we take your x value. We always plug in your x, right? F of x. 2, 2. So now we have 4. Again, this is the slope of the tangent line at 2, 4. So if we're just curious as to what your rate of change is here, or what your slope is of your tangent line at this point, we could finish. Now, if we wanted it a step further, because it does ask for the equation of a tangent line, it says use your point 1, 1 and the slope. In our case, our slope is 2. To create an equation of a line. So here we have your slope, m is equal to 2. We have your point, 1, 1. Now make an equation. Y equals mx plus b. Well, from here, right, we have y is 1, your slope is 2, x is 1 plus b, right? This is back from chapter 1.1. So now we can go ahead and start to solve. So 2 plus b, subtract the 2, b is equal to -1. Therefore, y is equal to 2x minus 1, which is exactly what we learned from previous. And you can see that line right here in red. Your slope, if we were to graph it, would be y is equal to 2x minus the 1 from your y-intercept. Now let's have you do it one more time with this one. Again, you have your point and your slope. So your slope has changed. Slope is now 4. Your point has changed to 2, 4. You want to make the equation y equals mx plus b using your points. So we have 4 is equal to 4 times 2 plus b. So you have 4 is equal to 8 plus b. Subtract your 8 to the other side. B is equal to -4. Therefore, the equation y is equal to 4x minus 4. Again, this isn't a perfect drawing, but it does look kind of close as if it were going to go past. Let's say this is -3. So that just means that here could be that -4. And that does kind of match up with this line. I know it's kind of hard to see when it's off the page. So to recap, right, take your first derivative. Step 2, plug in your point, your x coordinate, into your first derivative to get the slope. Step 3, use that slope and that point to find the equation. So let's have you try it all over again with example 4. Find the equation of the tangent line. Great. So see if you can pause the video. Let's see. We need our point. We need our degree to really show in an obvious way. So I'm going to bring up your degree into the numerator, and now it's negative. And actually, let me rewrite that. So now let's go ahead and take your first derivative, -2 x to the -3, right? Subtracting 1. We're going to rewrite this to say -2 over x cubed on the bottom. So this is step 1. Take the first derivative. Step 2, we said use the x value of your point. Your point is 2, 1/2. Use your x value. So when x is equal to 2, we're going to plug it into your first derivative. So your first derivative, we had -2 over 2 cubed, which is -2 over 8, which is -1/4. This is the slope of the tangent line. This is your m. Step 3, we have your slope and your point. So make an equation. And I can, if we need, at the very end, like go through it one more time as like step by step. We'll kind of make room for here. So step 3, you have m. You have your point. Let's go ahead and make the equation. So 1/2 is equal to -1/4 times 2 plus b. We can put this over 1 if we want. We have -1/2 is equal to -2 over 4 plus b. Add 1/2 to the other side. 1/2 plus 1/2 is just 1 is equal to b. So y is equal to -1/4 x plus 1. So kind of a brief overview. Step 1, take the first derivative. Step 2, plug the x value into the first derivative. Step 3, use your m and point to make the equation. All right, last page is just talking about different notations. So it says you'll often see d over dx, which is read as the derivative with respects to x. So x being the variable that we're interested in deriving, because in the future we're going to have many variables at play in which we're trying to derive at once. So in this case, we're just talking about the derivatives. So I want to derive, and I want to derive specifically my x variable. So different notations such as down below. You could also see d over dx of f of x means that we now have your first derivative. So this is talking about your first derivative. So if it says derive when x is x to the sixth, then you can go ahead and derive. This is now your first derivative. And again, once more, derive with respects to x. Therefore, when you derive, this is now your first derivative. So it's just saying in this notation, it's just saying that take the derivative of the variable, specifically the variable in which it wants. If it was y, we want to take the variable y derivative. If it's the variable p, we're going to take the variable p derivative. You may also see dy over dx when completing your derivation. So it implies that you have already taken the derivative of the function with respect to x. So at the very end, sometimes you can include dy over dx. So again, it just says derive the variable. So if you're seeing those notations, that is all it's implying as to which variable it is with given that particular function.